Hey, what's going on, guys? In this video we are going to see some problems on Boolean algebra, truth table, and also reduction of expression. Now let's look at an example. Let's say we have a expression that's given like this: f is equal to x bar y plus y bar z bar plus xyz, and if we want to know the final output, what's it's gonna be. Okay, now to find that one out, first we have to create the xyz table. In order to find, we have to find the final output using the truth table. So we have to have xyz because xyz are the terms used right here. So when we have three different terms, this is gonna be, we are going to have 8 different combinations because it goes like 2 power n. Since we have 3 different terms, 2 power 3, that's going to be 8. So we have to have 8 different terms. So it's going to go like this. We are going to have terms like 0 0 0, then 0 0 1, 0 1 0, then 0 1 1, and after that we will have 1 0 0, 1 0 1, 1 1 0, 1 1 1. Now how can we write this one easily? There's a pattern to this. You can see we have to have totally 8 numbers, okay, because 2 power 3 is 8 because we have 3 different terms. If you notice the first one, 0 1 0 1 0 1 0 1, right? And if you look at the second one, 0 0 1 1 0 0 1 1. So you don't have to think about it. The pattern goes like this. Then after that, 4 0 4 1, right? The next term is going to be what? If you have 4 terms, you will have 16 different terms because 2 power 4, that's going to be 16. So you will have 8 0 8 1, and after that 2 power 5 is going to be 32, so you will have 16 0 16 1. So the pattern goes like that. So you don't even have to think about writing this order. You can just write 0 1 0 1. You have to remember you will get 8 numbers, and then 0 0 1 1 0 0 1 1, and then 4 0 4 1, and that's how we can write this order. Now let's see how it works. Here we have let's look at the final output. I can directly put the final output, but there's another way to do this in a longer way. But let's look at the direct method. So when we have AND x bar y, like when we have 2 terms together, that means ANDs, right? So in AND we cannot have any 0 in order to get 1. Like if one of the term is 0, then the whole thing is 0. So both of them has to be 1 in order to get 1. So let's look at the possible situations we can get 1. In order here we have x complement. X complement means if x is 0, this is going to be 1, and if x is 1, this is going to be 0. This is opposite of whatever the x value we have. So what we have to have is we have to have 0 for x value, and y has to be 1 because if x value is 0, the complement is going to be 1, and if y is also 1, then we are going to get the output 1. So first we have to look at that one, because this one, we are adding these 3 together. This is like these 3 are OR, right? So if one of them is 1, all of them are going to be 1. In OR gate, if one of them is 1, all of them are going to be 1. But in AND gate, if one of them is 0, all of them are going to be 0. These are the 2 things we have to remember. So if we find the possible ones for this one, we can directly put that. So let's see, for this one to be 1, we have to have x to be 0 and y to be 1, because if x is 0, the complement is going to be 1. So 1 1, that's going to give us 1. Now let's look at this one. Here we have, let's see, this one matches, right? Because x is 0, y is 1. So this is going to be 1. And this is also x is 0, y is 1. So this is also going to be 1. And we don't have any other situation where x is 0, y is 1. Okay, so let's leave it for this one. Now let's look at this one. Here we have y bar, z bar. Y bar means y complement, z complement. So if y is 0 here, it's going to be 1 because complement means opposite. So y has to be 0 and z has to be 0 in order to get 1. Now let's see where we have y is 0 and z is 0. Here you can see the first one, y is 0, z is 0. So this is going to be 1. And here we have y is 0, z is 0. This is also going to be 1. And let's see the next one. So these are the only two things that have 0, right? Y and z is 0. Now the third term, we have to have all of them to be 1 because we don't have any complement. So they are direct x, y, z. So we just have to have all of them equal to 1 in order to get 1. So this one is the only one that has all of them 1. So this one has to be 1. Everything else is going to be 0. So these are the three things that we have to have, otherwise we are going to get 0. So these three are going to be 0. So this is going to be the final output of this expression, the given expression. Okay, now this is shortcut, and if you don't like this way, there's a longer way to do this. You can find this one individually and you can OR them together. So if I take x bar, y bar, I do the long method right now. So this is the final answer. Now in the long method we can compare. Okay, x bar, y bar, x bar, y. Okay, in order for this to be 1, we had to have x to be 0, y to be 1, right? X to be 0, y to be 1. This is the x to be 0, y to be 1. So this one is 1, and x is 0, y is 1. This is also 1, and we don't have any other things that has that, right? So others are going to be 0 for this one. 0, 0, 0, 0. Okay, so this is 1. Now the next one is y bar, z bar, y bar, z bar, and here we have to have both of them to be 0 because these are complements. So we are going to have the opposite. So if both of them are 0, both of them are going to be 1 because it's going to be complemented. So 0, 0, that's going to be 1. And here also we have 0, 0, that's going to be 1. Others are going to be just 0. So this is going to be 0, this is going to be 0, 0, 0 right here, 0 right here, 0 right here. Now let's look at the last one, x, y, z. So in order to get 1, we have to have all three to be 1 because we don't have any complement or anything else. So this is direct x, y, z. So we had to have all three to be 1 in order to get 1. So only that one, the last one is the only one that has all three is 1. So otherwise all of them are going to be 0. Now what we had to do is we had to OR them together in order to get the final output. That's our f. We directly did it before. Now from this one we are going to do it. In OR gate we had to have just 1, 1 in order to get 1. So here if we have 1 right here, this is 1, and if all of them are 0, that's 0. If this is 1, 1, 1, 1, 1, 1, and this one is 0, this one is 0, this one is 1. So here you can compare this one and this one, right? Before we did in shortcut way and got the same answer, but this is longer method. You can express each one individually and write the final answer. But this is good if you have like complicated situations. We will see in the next example. This one will be good in those kind of situations. But if you can directly see it, it's better. It's okay to do it directly. Okay, now let's see how is the circuit of this one going to look like. And here we have x bar y. So x bar y, this is AND gate. X bar y mean x is complemented. Complement mean we have to put a NOT gate right here and connect this one. This is x, and if you put a 0, that's going to be 1 right here. Okay, that's what complement mean. It's going to give us the opposite. And the next one is y connected to it, and here if you put 1, that's going to be just 1, right? And the output, if you put 0 and this is going to be 1, 1, 1, that's going to give us 1. And then y bar, z bar. Y bar, z bar is another AND gate. Both of them are complemented. So NOT gate, we have to connect two NOT gate. So what's going to happen is if you put 0, 0, this is going to be 1, 1. Finally you will get the output 1. Okay. And the next one is x, y, z. So here we have x, this is y bar, z bar. This is x, y. This is x bar, right? This is x bar, y, and this is y bar, z bar. So I shouldn't write bar right here because when I put, this is actually y and z connected to the NOT gate. So that's going to give us y bar, z bar. And then the last one we have to put, the last one is x, y, z, right? So this is x, y, z. And we have to have all of them to be 1 in order to get the final output 1. So 1, this is x, y, z. And all of them are combined to an OR gate. OR gate, because addition of all these three is the OR gate. When we add, that mean OR gate. Plus mean OR gate, right? So this one is the final output. That is what you are looking for. The F is the final output from all these three. Okay. And this is the first one. Now let's look at another example. Let's get rid of this thing. Okay. Let's get rid of all of these things. And let's look at another example. Let's say we have this expression. G is equal to xy plus x bar plus z plus y plus z bar. Okay. Now here I'm going to do the longer method, because these things are a little bit complicated. So you have to do the longer method. Now let's go ahead and do the longer method. Let's create a table for this one. Okay, here I'm going to have some charts. First we have to have XYZ combinations, because we have three different terms, XYZ combinations and XY, and also we have to have X bar Z, and then Y plus Z bar. Then we have to have multiplication of these two, and finally we will get our result. Okay, now let's do individually. So first let's go with the combinations. We have three different terms, XYZ. So as we seen before, when we have three different combinations, it's 2 power 3. So we are going to have, when we have three different terms XYZ, we are going to have 8 different combinations, because 2 power 3, that's 8. So we are going to have 8 different combinations, and the easy way to write the combination is to just write 0 1 0 1 0 1 0 1. Make sure you get 8 numbers, and after that it's going to go like 0 0 1 1 0 0 1 1, and the last term will go like 0 0 0 0 1 1 1 1. So these are the combinations we are going to have, and after that we have to find the first term. This is XY. So let's see where we are going to get 1 for XY. So in order to get 1, we have to have both of X and Y has to be 1, right? Because this is the AND gate. We have to, in order to get 1, both of them has to be 1. So X by 1, these are the only last two terms have X by 1. So these are the only two terms we are going to have 1 right here. Others are going to be just 0. 0 0 0 0 0 0. Okay. Now let's look at the next one, that is X bar plus C. X bar plus C. In order to get 1 in an OR gate, if one of them is 1, then we will get 1. So first let's look at this one. Let's look at X bar alone. If X bar is 1, then we will get a 1. So if X is 0, then X bar is 1, right? So this is 1, this is 1, this is 1, this is 1. And others are going to be just 0. So we don't have to worry about that one. And also if Z is also 1, we will get a 1. So Z is 1 right here, 1 right here. And also here we are going to have 1. And the last one also 1. So these are the possible terms. We are going to get 1 for X bar plus C. Now let's look at Y plus Z bar. Same thing. If Y is 1, we are going to get 1. Or if Z bar is 1, we are going to get 1. So here Y is 1 in these two terms. So here Y is 1, here Y is 1. And also in the last two Y is 1. And Z bar mean if Z is 0, we are going to get 1 because it's a complement. So if Z is 0, we are going to get 1. So Z is 0 mean complemented, that's 1. And here, 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 1, and that's it. And that's the others are going to be 0. So we are going to have 0 here, 0 here. Now the next thing is we have to AND them together. So we have to have X bar plus Z times and ANDed with Y plus Z bar. So let's see what we get if we do that. X bar plus Z and with Y plus Z bar. So if one of them is 0, we will get a 0, because in AND gate, if 1 0 is there, all of them are going to be 0. So this one, both of them are 1, so we are going to get 1. here we have 1 0, so this is 0 1 1. Here we have 1 0 0 1 0 0 1 0 0, and this is 1. So this is what we are getting from adding these two together. Now the last one is we have to see what we will get: xy plus x bar plus z, y plus z bar. Okay, so we found out this and now we have to OR with this one. If we OR with this two together, and if one of them is 1, we are going to get 1. So this is 1. Here we have 1 1. The second one is 0, and the third one we have a 1 right here, and in the fourth one we have 1 right here, and the fifth one both of them are 0 0, and the sixth one both of them are 0 0. In the seventh one we have 1, eighth one we have 1. So this is going to be the final output of G, and that's how we derive that. Okay, now let's look at another thing that where we asked to reduce a function, reduce a given expression. Okay, let's look at that example. Let's get rid of this one. Okay, so let's say the given expression is this: x bar z plus x y bar z plus x y z, and we want to reduce this one. So whenever we try to reduce, the first thing is we have to see whether we can take two things common. If we can't take two things common, we can simplify the other one. So here if we take, here you can see this x and z common for this. So if I take x z common, this is going to be y plus y bar. So y plus y bar mean what? One is complemented. So if one is 1, the other one is going to be 0. If this one is 0, the other one is going to be 1. It means we are going to have 1 of 1, right? One of them is going to be definitely 1. So it means this is definitely going to be 1, because in OR gate we just have to have 1 1 in order to get 1. So this is going to be x bar z plus xz multiplied by 1. It means we are going to get the same thing, but here we can do another thing. Here you can see, if we take z common, we are going to have another term like x bar plus x. Here we have a complement and also x. So it means here also we are going to have a 1 right here. We are going to definitely get a 1. So it means we can write this one as just z times 1. That's going to be just z. Okay, because in OR gate we just have to have 1 1 in order to get 1. So this is going to be the final results. And if you go ahead and draw the circuit for the previous one, design a circuit based on this, you are going to have a circuit like this. You are going to have an AND gate, this an AND gate, and in this one we have x complemented, it means connected to the NOT gate. So this is x, and then here we have z, and after that we have another one with 3 input AND gate. So here we have x, and then y complemented, y connected to the NOT, and then z. Okay, and the last one is xyz. So we have 3 input AND gate, and x is here, y is here, and then z is here. All of them are connected like this, and all of them are ORed. So it means connected to the OR gate. Okay, so this is the final output, and that's it, right? But here what it says is, when we reduce like this, instead of doing all this thing, we can only replace this one with a simple wire. Like this is the output f, but if we replace input c and replace this one with a wire, we will get a final output as f. So that's very simple, right? Instead of doing all this, adding all this AND gate and OR gate, we can connect a simple wire, and that's going to give us the same output. And that's why these things are very useful. Now let's look at another one where they are asking to find out equal output. Let's look at that one. So here the question is asking, giving some expressions like we have 3 expressions. F is equal to a bar c bar plus b c plus a b bar, and then we have g is equal to b c bar plus a bar. Actually this one is b bar c bar, a c plus a bar b, and this one also bar, and then the last one is h is equal to b bar c bar plus a c plus a bar b bar. So find equal output. Okay, let's see how we can find it. So in order to do this one, we have to use the truth table. Let's go ahead and create the truth table. So here we have the table, and in this one I'm gonna create 3 charts, actually 4 columns. Okay, 1 2 3 4. Okay, so we have 4 columns. In the first column we are going to have the combination. Here we have 3 different terms, right? We have a, we have b, we have c. So it means, so when we have 3 different terms, how many combinations we are going to have? 2 power of that. So we are going to have 8 different combinations. So as we seen before, when we have 8 combinations, like the combinations can be easily written as like 0 1 0 1 0 1 0 1 without thinking about it. You just have to make sure you get 8 different things. We have 8 numbers, right? Then the second one is going to go like this: 0 0 1 1 0 0 1 1, and the last one will go like 0 0 0 0 1 1 1 1, and that's how the combination look like. Now we have a, b, c. Now let's look at the function f. So in order to get 1, what has to happen? We have to have this one has to be 1, or this one has to be 1, or this one has to be on 1, right? So if one of them is 1, we will get a 1, because this is all of them are ORed, all these 3 are ORed, so we have to have 1. But in each of these 2 are ANDed, so it means these 2 has to be 1 in order to get 1 for this one, and for this one this b and c has to be 1 in order to get 1, and for this one a and b bar should be 1 in order to get 1. So in order to get 1, what we have to have? We have to have a and c 0, because this is complemented. If a is 0, that's going to be 1, because a complement is opposite, right? So we have to have a and c to be 0 in order to get 1. Let's see whether we have a and 0, c is equal to 0 anywhere. A and c 0, so this is going to be 1. And for this one, a and c 0, this is also going to be 1. And we only have these 2. Now let's look at the position where we have b and c is equal to 1. If these 2 are 1, we will get a 1. b and c 1, we have 1 right here, and the last one is also 1, right? And the next one is a has to be 1, b has to be 0, because b is complemented. If b is 0, that's going to be opposite, and we will get a 1. So let's see whether where we have a is 0, a is 1 and b is 0. A is 1, b is 0, this is 1. A is 1, b is 0, this is 1, and that's it. Others are going to be 0. Now let's look at g. For g to be 1, or like any of these 3 has to be 1. In each of these 3, b bar, c bar should be, both of them should be equal to 1. Like if b and c are 0, we will get a 1, because this is complement. It's going to be opposite, right? Now let's see where we have b and c is equal to 0. B and c are 0 here, so that's 1. And here we have b and c 0, that's 1. And that's it. So these are the 2 terms. And let's look at the next one. A bar, c bar. Both of them has to be 0 in order to get 1. A is 0 where? Here. A and c 0. A and c 0. A and c 0. So this is also 1. A and c 0, we don't have any other places, so these are the 2 terms. The next one is a bar, b bar. So a has to be 0, b has to be 1. A has to be 0, b has to be 1. So this is 1. Oh, b, not c. So this is wrong. A has to be 1. A has to be 0, b has to be 1. A has to be 0 and b has to be 1. I think I made a mistake previously. In the previous one we have a bar c bar. Okay, let me do, I think G I had to do all over again. I made a mistake. B bar C bar, both of them has to be 0 in order to get 1. B bar C bar 0 1. Here we have 0 1. A bar C bar, both of them has to be 0 in order to get 1. A C, this is 1, and we don't have anything else. A bar B. Okay, actually I copied this one wrong, that's why it's a problem. This is A bar C, but it doesn't matter. But if in this way you will get a similar answer like other one, but you will see finally. A bar C, if A, here we had to have A is equal to 0, C is equal to 1, right? A is equal to 0, C is equal to 1. A is equal to 0, C is equal to 1. A is equal to 0, C is equal to 1. This one is 1, okay? And A is equal to 0, C is equal to 1. So those are the only things we have right now. It looks like that's about it. So others are going to be just 0. So this is 0, and this one is 0 0 0. Let's look at the last one. B bar C bar. B has, both of them has to be 0 in order to get 1. So this is 1, and then here we have 1, and that's it. Let's look at the next one. A C. So we have to have A and C to be 1 in order to get 1. A and C 1 here. So this one is 1. A and C 1 here. This is also 1. And then A bar B bar. If A is 0, B is 0, this is 1. A is 0, B is 0, this is 1. And then that's it. B bar C bar, A C, A bar B. This one is B, not B bar. So I had to do it all over again, because if I do like this I won't get a similar answer. So I have to have an equal answer to compare, like to prove we can have something similar. Okay, B bar C bar. B bar C bar mean what? Both of them has to be 0 in order to get 1. So this is 1, and then this is also 1. A C, both of them has to be 1 in order to get 1. So this is 1, and this is also 1. And A bar B, A has to be 0, B has to be 1. A has to be 0, B has to be 1. So this is 1. And A has to be 0, B has to be 1. A has to be 0, B has to be 1. A, C. Okay, let me see if I am making any mistake. 0. This combination, this is suspicious. A and C. Okay, I missed it here. A and C, if A and C are 1, this one is 1, right? This is 0. Now you can see these two are equal. These two are equal. So when we have this expression, that makes this one equal. Previously I was changing things, like I was changing the expression, but it doesn't matter, like you can have the wrong answer too, right? But I just want to show you, like we can have equal expression for different terms. That's why I was changing and finding the equal one, right? Now we have equal expression, like we can have equal output from different expressions. That's what I want to show. And that's it for this one. And let's see some other examples. Let's see another one. We can reduce an expression. Let's get rid of this one. Okay, let's say we have a expression like this: x bar y bar c bar plus x bar y bar z plus x bar y z plus x y z plus x y z bar. Now the question here is asking us to reduce this expression. Now let's go ahead and do that. Let's see how we can do this. The first thing is we have to see whether we can take two things common. In the first two, x bar y bar is common, so we can take that one common. X bar y bar common, so this is going to be c bar plus c. C bar plus c is what, like when we have OR gate, if we have a complement and the original form, it means that's a 1, because if this is 1, this is going to be 0. If this is 0, this is 0, this is going to be 1. So it means we are definitely going to have 1. It means the whole thing is 1, because in OR gate we just have to have 1 1 in order to get the answer 1. So this is going to be just x bar y bar, because if you multiply x bar y bar with 1, that's going to be just x bar y bar. And in the next one, we can take x bar c common. So x bar z common, this is going to be y bar plus y. Again, that's the same thing. We will get x bar z, because this is y and y complement. And here we have x, y. So we have taken this. We have taken these two. So we are left with this one. But here we can do a trick. We can add one more x, y, z. In that way we can reduce this one too, because when we have, like if you remember OR gate, when we have a plus a, the final answer is a, because no matter how many times you add, you are going to get a. So you can put another xyz, because we already have xyz. You can put another xyz, that's going to be the same. So here what we can do is, if we put xyz, we can take xy common again, and that's going to give us c bar plus z. In that way we will be left with xy. So here we are going to have xy. So this is going to be the reduced form. And if you draw the circuit for this one, it's going to look like this. First we will have x bar, x and y are complemented, so we have to connect this one to a NOT gate. Complement mean NOT. So this is going to be x connected to the NOT gate and also y connected to the NOT gate. Both of them are ANDed together. That's why we have AND gate right here. And this is y. This is y. And then we have x bar z. X bar z. So x is not connected to the NOT gate. That's why x complement, we have x complement. And then z. And after that we have x and y. So this is x. And here we have y. And that's it. All of them are ORed together. Okay. And that's going to be the final output. Okay. So this is going to be, this is how the circuit is going to look like. Now the next thing is we can simplify, like we can, this is not the only way. You can do the reduction in many different ways. Let's look at another example. Let's do the same thing in a different way. Here instead of this one, what we can do is, so let's write the function again, expression again. X bar y bar z bar plus x bar y bar z plus x bar y z plus x y z plus x y z bar. So this was the expression. Now here one thing we can do, here you can see x bar is common. We can take x bar common. If we do that, this is going to be left with y bar z bar plus y bar z plus y z. And then here you can do one more thing, x bar and then y bar z. Yeah, y bar c is left, y bar c bar is left, and here we can take z common. If we take z common, this is going to be y plus y bar. Okay, that's going to give us x bar y bar z bar plus z, because this is going to be y plus y complement, that's going to be just 1. So we are going to have y bar z bar plus z. So in this one, whenever we have an expression like this, there's a rule says that if you have a plus a bar b, you can replace that one with a plus b. So if we treat this one as a, and this one is a, and this one is a bar, and this one is b. Okay, actually b, yeah, treat this one as b. So we are going to have a plus b as output, right? Like we can represent a plus a bar b as a plus b. So the finally we can express this one as x bar. A plus b is going to be what? Z plus y bar. So we can write this one like this. And then if we do that and expand this one, this is going to be x bar z plus y bar x bar. Or we can write x bar y bar, that way it looks better. X bar y bar, and then we are left with, we took these three terms, right, combine them together, we are left with this one. So that's going to be xy common z plus z bar, and that's going to be another one. So finally we will get the expression like x bar z plus x bar y bar plus xy. So here you can see this answer and this answer. These are not equal. We are getting different expressions. So there are different ways you can simplify the same expression in different way. And that's how we do that. I hope this helps. Thanks for watching.